Hello students, so let us continue. Let us start with the ionic mobility. Ionic mobility. So as the name suggests, ionic mobility related to the speed of the ion, how a particular ion moves in a solution. Now it is observed that the different ions move differently, based on their size, also a influencing factor. So how an ions move, what is the speed of the ion? That part we talks in ionic mobility. It is observed that even though HCl and NaCl both are strong electrolytes. Strong electrolytes, they are containing a common ion, that is Cl minus ion. You can see. Now you imagine at infinite dilution. We have already discussed not infinite dilution. No, they are actually free from all kind of attraction because so many volume is available. So infinite dilution means they absolutely can independently contribute to the molar conductivity. So look at here, even though anions are same, the difference is in cation, still the molar conductivity of HCl and molar conductivity of NaCl is different at infinite dilution. So what does it suggest? So that suggests that the cations and anions have different ionic mobility. Based on the ionic mobility, they have different molar conductivity. So it's observed that HCl have higher molar conductivity at infinite dilution compared to NaCl. That suggests that H plus ion is smaller in size and they have greater mobility, ionic mobility compared to Na plus ion. Hence, they exhibiting different molar conductivity. So here, we can understand that the molar conductivity is always proportional to the related to the speed of the ion, and higher the speed of the ion, generally the molar conductivity will be higher as well. So let us define ionic mobility. Ionic mobility, you can now define it by the speed of the ion. Speed of the ion. Now we can express either in centimeter or second, or centimeter or in meter. So centimeter per second divided by, it's always proportional to the potential as well. It depends on proportional as well. So potential gradients, potential gradient applied in volt per centimeter. So now here we express the ionic mobility in terms of centimeter. That means distance not traveled. Let it be in centimeter. Speed of the ion divided by potential gradient applied in volt. Will give you the ionic mobility. So imagine a potential gradient is applied and the speed of the ion. We also know time. So taking the ratio will give you ionic mobility. So ionic mobility will be in the unit. Centimeter will come up means centimeter square. The unit we express here is centimeter square, volt inverse, second inverse. This will be the units for the ionic mobility when you express in terms of centimeter. Now the same thing if you express in meter, how will be speed of the ion in meter per second divided by volt per meter inverse. So ionic mobility you can also express in meter as well. That is SI unit. Ionic mobility, the unit will be in terms of centimeter, it will be meter. Meter inverse, volt inverse, second inverse will be the unit in SI unit. So that's now you can imagine about ionic mobility. It's related to the speed of ion. Remember, anions and cations also moving, and the movement is depends on the size of the ion, also the potential gradients. Next, now let us discuss next important theory that we will call Hittorf's method. Hittorf's method. So Hittorf's method is one of the important theory put forward by this scientist. It used to explain the transport number of a particular ion. Transport number, transport number of a particular ion. No, transport number you can represent as T plus means no transport number of cation, and T minus represent the transport number of anion. So what do you mean by transport number? Transport number means transport number means is a fraction of current carried by a particular ion. Fraction of current carried by a particular ion, that we will call transport number. Transport number you can independently express for cation and anions. So what do you mean by transport number? It's a fraction of current carried by a particular ion, which means no current carried by, if you talk about T plus transport number of cation, how can you express it is the current carried by cation, current carried by cation divided by total currents. That will give you transport number of cation. Similarly, current carried by anion divided by total current give you transport number of anion. So transport number, what's the significance of transport number? We already saw different ions have different mobility. So based on the mobility, they exhibit different conductivity. So how much a current carried by a particular ion, that always proportional to the mobility of ionic mobility. Okay, because no cations, anions may be different their size, they influenced by the potential gradient as well. So how fast an ion moves, that always proportional to the fraction of current carried by a particular ion. So the transport number is is a very important term that you can learn. It is the fraction of current carried by a particular ion. Remember, it's different for different ion. For example, talk about nitric acid. You imagine a dilute nitric acid is electrolytes. It's observed that H plus ion, which is smaller in size, carries the most part of the current. 0.84 part of the current is carried by this H plus ion, while rest 0.16 is carried by nitrate ion. Look at this. Talk about electrolysis of nitric acid, HNO3. H plus ion, which is smaller in size, carries the most part of the current. 0.84 part means more than 80 percentage, which is you can understand H plus ion moves such faster, and the bulk of the current carried by the H plus ion. While nitrate ion, it's very much less compared to H plus ion. It is NO3 minus. So this is not something that you can remember related to the transport number. It is different for different ions. So let us discuss the silent features of Hittorf's method. What was his important points. First point, the cations and anions get discharged in equivalent amount at respect to electrode, no matter what's the speed of the ion. That's a very important point. Something that you have to remember. You just imagine electrolysis of NaCl, molten NaCl. You imagine an anode is there, a cathode is there. Anode means the electrode connected to the positive terminal, and we taken molten NaCl. Molten NaCl. So Na plus ion, Cl minus ion will be there. Na plus ion moves to cathode, Cl minus ion moves to anode. So here now, what's the first point? The first point is cation and anion get discharged. Discharged means the charge has gone, right? So we know Na plus ion and Cl minus ion will be in there, in the electrolytic solution. And Na plus ion moves to cathode, cation moves to cathode, and anion moves to anode. So what happening during the electrolysis? After the electrolysis, you can see Na plus ion get discharged, become sodium metal. Charge was there. After electrolysis, you can see charge has gone. This is what mean by discharge. So Na plus ion, converted into sodium metal. This is one of the method of preparation of sodium metal. And also this is happening at anode. Sorry, this is happening at cathode, which means now electrode Na plus ion, electron is added, addition of electron is reduction, and that's what happening at cathode. So accepting an electron to form sodium metal. While in anion you can see Cl minus ion converted into Cl. Chlorine atom will be there. Since chlorine atom is not stable, 2 moles is required. So no, at a time 2 moles of electron is released, and at a time 2 moles of sodium ion is converted into sodium metal as well. This is something now we observe in electrolysis. The number of electron that is released at anode will be always proportional to the number of electron that is gained at the cathode. So at anode you can see the Cl minus is converted into chlorine gas, Cl2 gas I am talking about. Sorry, this is not 2Cl, it is Cl2 gas. Cl2 gas and 2 electron also release. Release of electron, oxidation. Addition of electron, reduction. So what's happening here? You just understand Na plus ion, cation moves to cathode, anion moves to anode. So the first point related to Hittorf method, no, the amount of the cations and anions, no, get discharged, or the amount of substance that produced, no, will be always proportional to the mobility, and equivalent amount will be produced irrespective of their speed. Maybe Na plus ion and Cl minus ion moved with a different speed. That's possible. No, you talk about NaCl no, maybe not that much large different, but talk about other different pair of cation and anion. Imagine they may be moved differently, but no, the amount of substance that gets discharged at their respective electrode will be equivalent, will be same, which means no. So Na plus ion, the amount of Na plus ion is forming will be always equal to amount of chlorine gas that is formed at anode, and sodium metal formed at cathode will be equivalent irrespective of the speed of the air. That's the first point. The amount of the cations and anion get discharged. The cation and anion get discharged. Discharge means no, after discharging, no, they producing some substance like sodium metal will be formed at cathode, chlorine gas will be formed at anode. So the cation and anions get discharged at their respective electrode. Respective electrode. The cation and anion get discharged at their respective electrode will be in equivalent amount. Equivalent amount, irrespective of the speed of the ion. Maybe the cations and anions have different speed, but it doesn't matter. The amount of cation and anion get discharged at the respective electrode will be always same. That's the first point. Second point, no. Imagine both cations and anions are there. So if only one kind of ion can move, concentration falls around that electrode having the same polarity. In other cases, concentration falls around each electrode. Now next point, now you can relate it to the fall in concentration. Fall in concentration. So here now a new term is coming, fall in concentration. What does it mean? Here now you have to imagine around this is anode I'm talking about, connected to the positive terminal. Na plus ion always moves to cathode. So there is a movement of cation towards the cathode, which means now around this anode the cation concentration always decreases because Na plus ion moves to cathode. Similarly, around this is anode. Around this cathode you can see chloride ion concentration decreases. This is something now that you observe in electrolysis. The concentration of cation decreases around the anode and the concentration of anion decreases around the cathode as well. So falling concentration of this falling concentration of cation and anion will be equal because no they're getting equally get discharged. So the falling concentration around each electron will be same. Now imagine only one particular ion can move. The movement of other ion is restricted by applying suitable electrode or like that. So if one particular ion moves, no, you have to imagine the falling concentration around that particular electrode will be again now proportional to the speed of the ion because Na plus ion moves to the cathode and Cl minus ion moves to the anode. So the point is if only one kind of ion can move, the concentration falls around the electrode having the same polarity. So there you can see a fall in concentration around a particular electrode, no, when electrolysis is carried out. So during the electrolysis, falling concentration falling concentration of cation observed around around anode. Similarly, no falling concentration of anion observed around the cathode as well. So that's another observation. The fall in concentration or decrease in concentration of particular ion you will observe during the electrolysis. So next point, fall in concentration around anode will be always proportional to the speed of the ion. So that's another point. The fall in concentration, the fall in concentration around anode will be always proportional to the speed of the cation. Hence you can write like this: fall in concentration around the anode will be divided by fall in concentration around cathode. Fall in concentration around cathode will be equal to fall in concentration of anode proportional to the speed of cation. Speed of cation divided by speed of cation divided by speed of anion. This is something now you can understand. The fall in concentration around anode will be proportional to the speed of cation. Look at here. What is a fall in concentration means decrease in concentration in Na plus ion. That will be proportional to the how fast Na plus ion moving. So fall in concentration around anode divided by fall in concentration around cathode will be equal to speed of the cation divided by speed of the anion. That's very important. Now. Equation related to the Hittorf method. Okay. Now let us discuss how we can determine the transport number. So transport number T plus means fraction of current carried by a particular cation will be proportional to speed of the will be always proportional to speed of the cation. So U plus divided by U plus plus U minus. So this is the equation that you can remember related to the transport number of cation. U plus divided by U plus plus U minus. What do you mean by U plus? This means this is speed of cation. Speed of cation, and U minus means it's the speed of anion. It is the speed of anion. So U plus divided by U plus plus U minus, that will give you T plus transport number of cation. Similarly, transport number of anion will be equal to U minus divided by U plus U minus. So this is the important point related to Hittorf method. The fraction of current carried by a particular ion always proportional to the speed of that particular ion. How fast it's moving, because no more faster it's moving means no more current it can carry. So that is the important equation that you can remember related to the Hittorf method. So if you ask her to find the if you ask her to write the principle that you can discuss like this: the fraction of current carried by a particular ion always proportional to the speed of the ion. Or you can you can imagine cation moves to cathode. So now how can you imagine cation moves to cathode means now concentration around anode is decreasing, right? So you can have an equation like this: T plus is equal to U plus U plus divided by U plus U minus. It is the total speed of the ion, right? So falling concentration around anode, falling concentration around anode divided by falling concentration around anode plus falling concentration around anode plus falling concentration around cathode. So this is the equation that you can remember. Actually, we using this particular equation to find the transport number, because the mobility of ion is always proportional to the falling concentration in the respective electron. So talk about T plus. How can you find T plus? You can use this equation: U plus divided by U plus U minus. This is the chemistry that we are using. Now using that, you can imagine the falling concentration around anode or decreasing concentration of cation around anode will be proportional to the speed of the ion. So you can use this equation. This is the principle. So falling concentration around anode divided by falling concentration around anode plus falling concentration around cathode will be equal to T plus. That directly will give you the transport number of cation. So using Hittorf method, what we are using, what we are calculating, we are doing nothing but we are measuring what is the falling concentration around anode. So what is the change in concentration before electrolysis, after electrolysis? Now what is the change in concentration around anode, and the total falling concentration around each electrode. Okay, that will give you an idea about the total current carried by each ion. So using this equation, you can find the transport number of a particular ion. This is the principle. Now let us discuss the experimental setup, how this has been done. Here now you can see, you just go through the picture. Here you can see two vertical glass tubes will be there, and which is now always connected to the stopcock will be there to control the motion. Stopcock will be there, and two vertical glass tubes. Okay, then the electrode that we always you can understand whether it's a positive electrode or negative electrode based on the which terminal of the battery that is connected. So this is now connected to this particular electrode connected to the positive terminal, and next electrode that is connected to the negative terminal. Remember, there is one more experimental setup is there. We connecting a copper voltameter. We are connecting a copper voltameter series to this electrode. Or you can draw beautifully looking at the picture. I'm just drawing the rough picture here. So here you can see a electrode will be there, a copper, this is we call copper voltameter. you will understand what's no significance of copper voltammeter. And no, that's connected to the negative terminal as well. So here now, this electrode now perfectly sealed. Inside you can see a electrode will be there. Now either you can use an inert electrode, or now you can use uh, a electrode of same type. So yes, electrodes are there inside a very narrow tube. Electrodes are there inside a narrow tubes in both the electrodes, and you can see, you just imagine what the solution field is. Silver nitrate, here we talking about no electrolysis of silver nitrate. So silver nitrate solution is filled, NO3 solution in uh, both the solution, and there is a no a U tube is also connected in between to prevent the intermixing. A U tube is there in between. A tube will be there, which is no stopcock also is connected, and the silver nitrate will be solution will be there, and stopcock will control the motion. Here also stopcock is there. You can imagine. So now here also solution, silver nitrate solution is there. This is the no, U tube which is now connected in between the anode and cathode. So these are the experimental setup. We talks about. It consists of two vertical glass tubes. Inside a small narrow tube is electrode is there. So a narrow tube you can see going through inside the glass tubes, and electrode will be there. Generally, inert electrode or the electrode of same type. For example, if you carried out electrodes of silver nitrate, silver electrode can be used, or no, the inert electrode like platinum can be used. So now a electrode is there which is connected to the positive terminal, which means this is our anode and this is a cathode, and now we connected a copper voltammeter in series to this, which means copper voltammeter is used to find the total fall in concentration around both the electrode, because now the amount of copper that get deposited at the copper voltammeter always proportional to the total current carried through the solution. So by according to Faraday's law, we know the total current passing through a solution is always proportional to the amount of substance deposited. The amount of substance that gets deposited. So using the Faraday's law, you can understand what is the total current that is passed through the solution by knowing the amount of copper that is get deposited. So that's that's why we connected a copper voltammeter to understand the total current that passes through the solution. So now let us now discuss the theory part, how we are calculating, what actually we know, the calculation part related to the this experiment. Here now silver nitrate solution, dilute silver nitrate solution is filled in the electrodes, and you can see electrolysis will be carried out around a current of 0.01. 0.01 to 0.02 ampere current is now passed through the solution for almost 2 to 3 hours. Current is passed through, and you can see the substance or cation moving to cathode, and anion moves to cathode, and in copper voltammeter you can see the copper start depositing once the electrolysis is carried out. Now once the current stop means the substance get deposited also stops. So these are the theories we know. Now let us discuss how we can calculate the transport number. For transport number, now using this particular point, the what is a fall in concentration around anode, what is the fall in concentration around cathode, that part now we are mainly focusing here. So anode, let's know the, let us go through the points. The weight of anode, weight of anode, the weight of anode solution collected after electrolysis, the weight of anode collected after electrolysis, weight of anode collected after electrolysis, let it be A, and the weight of silver nitrate present is, let the weight of silver nitrate present is B gram. B gram. So let's now we know the amount of silver nitrate is taking. So we just calculate how much weight the silver nitrate solution that is there. After electrolysis, let it be a gram, and weight of the silver nitrate, and silver nitrate solution means water will be almost will be there as well. So the weight of silver nitrate present, let it be B. In the silver nitrate solution, water also will be there. So weight of the whole anode solution, let it be A gram. Weight of silver nitrate solution, let it be B gram. So then the weight of water will be, weight of water will be A minus B. A minus B gram. Why? Because now the weight of whole solution, anode solution is A gram, and the weight of, let the weight of silver nitrate be B gram. So A minus B gram will give you the weight of water. Now let the number of equivalent of AgNO3 present in A minus B gram of water. Let the number of equivalent, number of gram equivalent that we talk about, number of gram equivalents of silver nitrates present in A minus B gram of water. Now let us take a specified amount of water. Now let it be A minus B gram, which means now we discuss that specified amount of water, how much a gram equivalent of silver nitrate is present. That how can you calculate? Always the weight of silver nitrate, that is B, divided by equivalent mass. 170 is the equivalent mass of silver nitrate. So B by 70 will give you the number of gram equivalent of silver nitrate. Okay, let it be not as Y. Y is the number of gram equivalent of silver nitrate after electrolysis. So now Y is the number of gram equivalent of silver nitrate after electrolysis. Y is the number of gram equivalent of silver nitrate after electrolysis. Similarly, now number of gram equivalent of silver nitrate before electrolysis we have to find. For that, now you imagine, let it be X. X is the number of gram equivalent of silver nitrate present in A minus B gram of water before electrolysis. Let X be the number of gram equivalents, number of gram equivalents of silver nitrates present before electrolysis, present before electrolysis. It will be X. What is Y? It is a number of gram equivalent of silver nitrate after electrolysis, and X is the number of gram equivalent of silver nitrate before electrolysis. So fall in concentration. So you can easily find the fall in concentration around anode. Fall in concentration around an anode. This you can find based on two points you have to remember. Once you consider the inert electrode like platinum is used. There's are two possibilities there. If the electrode use is no platinum electrode, you have to use no different logic. If the anode use this electrode like silver in the electrode, so silver nitrate, there you have to think differently. So basically, what you are doing in Hittorf method, we are measuring the weight of anode solution before electrolysis. We are measuring the anode solution after electrolysis because no some silver ions are moving to cathode. So after electrolysis we suppose no a decrease in concentration of silver ion if no inert electrode like platinum is used because there is the inert platinum electrode do not involve in reaction. So that's a point. So now just imagine now two cases where when platinum electrode is used, when platinum electrode is used, if platinum electrode is used, no, then what will be the falling concentration around anode? So how can you find the transport number? T plus will give you no falling concentration around anode divided by total falling concentration around each electrode. So this is basically now we are using the equation. So what is a falling concentration around anode? We know the X is the number of gram equivalent before electrolysis. Since it's a platinum electrode, no, it's a inert electrode that do not involve in any reaction. So the total gram equivalent of silver nitrate before electrolysis will be higher compared to the total gram equivalent of silver nitrate after electrolysis because after electrolysis some silver ion definitely will be goes to cathode. So the transport number of cation you can decide by falling concentration or decrease in concentration. What will be the decrease in concentration? That will be x minus y divided by let the total falling concentration around each electrode, let it be set. I take an set. So x minus y divided by set will give you the transport number of cation. So if you find transport number of cation, you can easily find the transport number of anion as well because T plus T minus will be equal to 1. Always no T plus T minus will be equal to 1. It is the if you got T plus 1 minus T minus 1 minus T plus will give you T minus as well. So remember having writing X and Y, don't get confused. Is what this all about. X is the number of gram equivalent of our electrolyte before electrolysis. Y is the number of gram equivalent of Y after electrolysis. So X minus Y will give you what is the decrease in concentration, what is the fall in concentration around anode divided by total fall in concentration that is set. No, if you divide X minus Y divided by set will give you the transport number of the cation. After getting transport number of cation, you can find the transport number of anion as well. Now remember the how can you find the transport number if a silver electrode instead of platinum electrode if we use silver electrode, what will be the difference? Here now one point a student has to remember, if silver electrode is used, no, the silver metal also no getting oxidized. Now silver is converted into silver ions. Now when silver electrode is used, that oxidation, removal of electron from silver to form silver ion also taking place there, which means no, yes, we are expecting a decrease in concentration around anode because cation are moving to cathode, but now around anode you can see a slight increase in silver ions after electrolysis because new silver ions are producing from the electrode that we used as silver electrode is used. So that's a point student has to remember. Now here if you want to calculate the decrease in falling concentration, one second. Okay, so here if you want to find the transport number of cation, here now falling concentration around anion will be X plus Z minus Y divided by Z. So what's the significance here? Here now Z will be equal to total falling concentration around cation and anion, or the total fraction of current carried by both ion. So here remember, some amount of cations are moving towards the cathode. Yes, there is a falling concentration definitely takes place at anode, that is taking place there. But now what is the movement of ion? How much silver ions are moving towards the cathode? That you can understand by from this value of Z, because an equivalent amount of substance will be produced at the cathode as well. So having this equation X plus Z minus Y have to be used, because here anion concentration is slightly increasing because of the silver electrode is used. So if you want to exactly measure the falling concentration around anode, even same electrode is used, here you have to use X plus Z minus Y. That will give the effective decrease in concentration around anode, divided by total falling concentration. If the inert electrode like platinum is used, you can simply use X minus Y divided by Z. But here a silver ion concentration found to be increased after electrolysis, simply because silver ions are produced from silver electrode. Because of that, now what is the exact falling concentration around that anode after the electrolysis? Now you have to think like this, where now you have to add X plus Z. X is it is the number of gram equivalent of silver nitrate before electrolysis, and Y is the number of gram equivalent of silver nitrate after electrolysis. Now here you have to find exactly what is the falling concentration around anode. For that, now you have to think which particular ions are what is the total concentration of ions that is moved to the respective electrode. That you have to find. Okay, because you cannot think the amount of ions produced, because that has to be minus. That should be minus, right? So X plus Z minus Y will give you what is the what is the silver ion that moved to the cathode, and that's will give you the falling concentration. Effective, that's the word I would like to use. Effective falling concentration around anode divided by total falling concentration will give you the transport number of cation if silver electrode is used. So this is the theory related to Hittorf's method. So please go through the chapter. It's very important that you have to follow each class, otherwise it will be difficult to follow uh, each point. So next class we can do the problems related to this, and next theory also we can discuss, that we call moving boundary method. Okay, thanks for listening. Let's find out.